So let's
Okay.
start. So welcome everyone. Thank you for coming late Friday afternoon. So we're very happy to have Justin Burkett from Georgia Tech, and Justin will speak about statistical uncertainty and coarse contracts. So Justin, as I said, we go for about 60 minutes, but you can take up to 75 minutes. Okay, all yours.
Okay. Thank you very much for having me. This is a project that, excuse me, that Max and I completed last year. Max is also at Georgia Tech. And it's part of a kind of a larger program that Max has started and I've sort of joined on to around taking the role of data a little bit more seriously when we're talking about designing mechanisms. So the basic idea is that we're very used to specifying a source of uncertainty in our problems, and we usually take the Bayesian approach and say that people have priors over these unknowns. But in in most cases in the real world, we are told to use some sort of data to make inferences about what we are unsure about. What we want to do, and what Max wants to do starting from his dissertation, is to make the role of data more explicit in determining how beliefs come about. Okay, so what we were doing in this paper is we were looking at building a sort of a data-based inference problem into a traditional moral hazard problem, a la Holmstrom, and we were looking at whether or not we can resolve one of the awkward features of the Holmstrom model. Okay. Here's the basic motivation. Hopefully you all are familiar, although I will go through the basic setup of the model in just a bit. In Holmstrom's model, with a risk-averse agent, and it will be important to consider a risk-averse agent here, and I'll tell you why in a minute. Basically, we have two conflicting issues that the principal has to deal with. We have a principal and an agent. The principal is designing a contract for the agent in order to motivate them to exert some effort, which the principal cannot observe directly. And the two conflicting motivations are that the principal needs to incentivize this effort on behalf of the agent, but they also, because of the risk aversion of the agent, want to mitigate the amount of risk. And the result is that we end up with very detailed contracts that are kind of very precisely tailored to the environment, and don't only pay where necessary, more or less. But if you sort of casually look around or read some empirical studies of people who do this sort of thing, contracts in the real world do not appear to exhibit this level of precision with respect to signals in the environment. And our motivating idea here is that this precision is naturally hampered in real world situations by needing to do things like using finite data for inference about perhaps the output technology. Okay, so the idea that we're going to look at here is to what extent can we formalize this idea that when the data being used by the principal is finite, they are not going to be able to, or not going to want to, I should say, write such precise contracts for the agent. Kind of the underlying motivation for this paper, as well as this sequence of papers that Max has been working on, is that we could look at this, you often look around and see empirical work that is based on theoretical models like auctions and things like that, that take kind of take the model as given and use data from an outside third-party perspective to estimate the unknowns of the model. People do this all the time with respect to first price auctions, for example. That would be the case if we had full confidence in the assumptions of common prior between the players interacting. You would get a different result, right? In terms of, you might get a different result, and we show you get a different result with respect to how the game is actually played if the players themselves have to use data to make inferences about what is happening in the environment. Okay, so we want to look at how problems associated with finite data inference influence the design of the contract itself. Okay. And by the way, feel free, anybody, to interrupt if you have questions as we go. Okay, so just to put it a little bit differently, the paper studies the implications of objective data constraints, kind of formal data constraints on how complex contracts are in this principal agent problem. We're going to effectively generate the beliefs, or have the beliefs in our model come out of publicly observed IID data on output. We need to be careful, and we spent a lot of time thinking about this as we were writing this paper. We need to be careful about exactly how this will work. We, in the process, discarded a lot of different ideas for models about how to set this up. I'm not sure that we have the perfect one here, but we have one that we think is at least better than the ones that we're not presenting here. So we have an agent who is going to, in order to exert effort, is going to demand that the data justify their choice of effort, and I'll be clear about that in a minute. The main result that we're going to focus on, or the element of this model that we want to focus on, is that these detailed contracts are going to be offered by the principal only when essentially sample sizes are large, only when the data kind of supports this level of precision with respect to the inferences that you can make. Alternatively, when there's not very much data, or the data doesn't support this level of detail, we're going to show that contracts will be coarse. So this is the language we're going to use: detailed versus coarse. Coarse contract being one that will typically pay the agent the same amount across a number of different outcomes. Okay, so you'll see portions of the contract that are constant over the realized output. Okay, so just to give you a preview, here is a picture of the types of contracts that are going to come out of our model. Let me explain the graph here, and hopefully the details will become clear as we go along. We're actually going to work in, it's not terribly important, but it does make the math easier. We're going to work in utility space. So the U1, U2, U3, and U4 lines correspond to the agent's ex post utility from different levels of output. So U1 is going to be the lowest output realization in this example, U2 the next lowest, and then U4 being the highest realization of output. The epsilon here is going to measure the level of uncertainty with respect to the finite data inference problem in the problem. So when epsilon is 0, that's going to reflect the full confidence in the empirical distribution that the agent is working with. So epsilon is 0 is going to correspond in our results to kind of this the most detailed version of the contract. So most detailed version of the contract is going to be reflected in the principal paying the agent a different amount for each level of output. So we have full separation in the output states. Now, as epsilon grows, this is going to correspond to the agent having less and less data, Or there's one other parameter that we can play with, which I'll introduce in a minute. So as epsilon is growing, think of this as the amount of data available is shrinking. And as that happens, the principal is effectively going to start to bunch output states together and coarsen the contract. So in this particular example, the most, there are just 4 known output states. So paying the agent 4 different wages effectively, or giving them 4 different utilities corresponds to the most possible detail. And then on the other extreme, as epsilon gets large enough, we'll eventually get just 2 different payment amounts. Why 2? Well, the principal still needs to motivate effort on behalf of the agent. So they still need to pay them make at least two different payments in order to get the agent to exert effort. And by the way, these epsilons will be in probability space. So you can think of 0, 0.01, 0.02, 0.03 as reflecting measures of probability. Okay. All right. So let me. Yes, go ahead.
Can I ask a question? So
yes, absolutely.
What is data in this model? So what does firstly, is it a dynamic model? Like is it a continuous time model, or is it a static model, or what does data consist of?
Sure. Data. So this is a static model, and these are comparative statics that we're looking at. There's no dynamics in the model.
Okay.
We're in a sense taking a basic Holmstrom model and replacing the informational assumptions in the Holmstrom model with new ones, and then also at the same time modifying the way that the agent and the principal behave with respect to these new information assumptions. The data is going to be we're going to look at basically a finite data set of output realizations related, where we're going to be able to see kind of we'll see n output realizations when the agent is exerting effort, and then we're going to see a different n perhaps number of realizations of output when the agent is not exerting effort. Does that make sense? Okay. And as always, I think when you're trying to come up with a new model for something that for a new way of thinking about a model that has been around for a very long time, there are going to be some compromises that we're going to have to make. I'm going to try to convince you that, and this has been discussed at length, that there are difficulties with the Holmstrom model as well. So it's not that we're ruining a perfect model or anything, but there are certainly a lot of trade-offs and decisions that we can make along the process. So I will try to indicate kind of the models that we didn't entertain and why we didn't entertain them as well. Okay, so here is one way of looking at a sort of a canonical moral hazard problem. And this is going to be a 2-effort problem. So and this will also allow you to get somewhat familiar with the notation that we're using throughout the paper. So we have an agent is going to choose low or high effort, and they're going to produce some amount of output in this capital mega. Now, in the canonical, in the Holmstrom setting, the output generating process, the way that the agent can turn effort into output, a distribution over output, is common knowledge between the principal and the agent. The principal is going to pay the agent with some contract W. W is going to map realizations of output to wages for the agent. The agent is strictly risk averse in the standard setting. And by the way, let me just make this comment. I'll probably make this comment a couple of times as we go through. Risk aversion is important for us because we are talking about, we want to talk about the level of detail being large in the result of the Holmstrom model. And that really only comes out when the agent is risk averse. When you have a risk neutral agent, you have a lot of freedom as the principal in the standard setup to play around with the level of precision. And if you like, you can often just pay the agent using a binary contract. So this idea that Holmstrom contracts require detail is only true if you have this risk-averse agent. Okay, so we're going to have a risk-neutral principal, and we are going to set this up so that the principal wants to incentivize high effort over L, so that'll be the incentive compatibility constraint, and also they want to choose the contract over some outside option. So that sets out the principal's problem as follows. Since we know that we want high effort, we can write this as minimizing the expected wage payment to the agent, subject to these incentive compatibility and individual rationality conditions. The only thing besides maybe, the only thing that may be non-standard about this presentation, although please ask questions if something is unclear, is our use of the deltas. The delta IC term is capturing, you can think of that as capturing the difference in effort costs between low and high effort. And this delta IR is soaking up the value of the outside option to the agent, as well as perhaps the effort costs associated with choosing high effort. Is that clear enough? Okay. All right, so here's what you get out of this problem. I hope many of you are familiar with it, at least at a high level. This is the kind of standard Holmstrom formula written in our notation. So what we have is you have a term on the left-hand side related to the marginal utility at each wage payment. So W star of Y will be the wage payment made at some output level Y. And the prescription from Holmstrom's problem is that you essentially vary the wages according to what is usually called the likelihood ratio. This ratio in green is the difference, it's the difference in the probability that we might observe this particular Y at high effort versus low effort divided by the probability of high effort. That lambda is just the Lagrange multiplier on the IC constraint, and then the mu term is the corresponding multiplier on the IR constraint. So our focus in this paper is, again, going back to the motivating idea, what we're looking at is that this contract being offered by the principal is supposed to be sensitive to the likelihood ratio, and this likelihood ratio, besides being different for each level of output, that's my second point here, it's very sensitive to the probabilities with which the principal and the agent assess the different output levels. So in particular, when this pi of y given h is small, you might see very large likelihood ratios, and this formula indicates that we should see correspondingly large payments or small payments, depending on the value of this ratio. And it is precise in the sense that it needs to vary carefully with respect to this likelihood ratio. Now, this model is the workhorse model. It's very famous, of course, but there are still gaps between the theory and the application. On the premises of the model, and this is the point that I highlighted in green earlier, we make this assumption of a common prior, which greatly simplifies the math and the presentation of the model, but still lacks foundations with respect to the decision theory that Savage set forth. in the sense that in Savage's theory, these probabilities or the priors themselves are idiosyncratic objects in the sense that they reflect perhaps heterogeneous assessments by each one of the agents. So this common prior assumption represents somewhat of a leap with respect to Savage's original model. And then we could also look at the prescriptions of the model. And as I've said before, the contracts we see in the real world don't seem to exhibit the level of detail that the model would suggest that they need to have, in the sense that they are not, that we don't look around and see wage contracts that are fully contingent on the state of the world. So what we're gonna do here is we're gonna modify the model essentially by adjusting this common prior assumption to reflect data that might be gathered by these by the principal and the agent. Okay, so we're going to work with a set of outputs, omega, that is finite, and hence we have a discrete sigma algebra. We're going to be able to observe for each level of effort, and here we're going to have 2 throughout the model, a finite sample of output from some unknown true technology that the agent possesses. In terms of beliefs, we're going to have to make beliefs assumptions about both the principal and the agent. We are going to follow some of the prior literature, which hopefully I will get to discuss at the end here, and assume that the principal selects a particular distribution that both parties are going to see as valid given the data. In particular, we're going to look at the principal choosing the empirical distribution, and they're going to evaluate their expected payments on the basis of this distribution. If you have questions about
Justin,
that. Yes,
yeah,
please.
Hi, Justin. Could you clarify bullet point 2? I mean, what is the interpretation for the true technology here?
So there's.
Am I audible? Yeah.
Yes. Thank you. So the technology. So we're thinking of sort of a data generating process that is at work generating these output samples, but is not being directly observed by either the principal or the agent. So if the agent exerts high effort, there is some technology that is determining the probability with which output is 5 or 10 or so on. Does that make sense, or is that your question?
Yeah, but these are nothing like histories of actions by the agents elsewhere or something like that, right? I mean,
No. So yes, so we're not looking at a dynamic a model at all.
No, true. I mean, but I mean, I'm thinking like, I mean, if we think of a pool of agents or something like that, like typically agents of this kind would have done this. We are not even going for such an interpretation of this technology, right? I mean, when you say effort is getting mapped to an outcome.
Yeah, so I think one way of thinking about this, and this is actually an interpretation that we're working with in another paper, which we haven't finished yet, is to say that the principal looks at what, maybe this is what you're suggesting, but the principal looks at what another agent has done in response to a contract that generates effort. And that's where, and they are operating under the assumption that this new agent that we're offering the contract to generates output with respect to the same technology. So the technology technology is just the distribution of output given the effort. Does that make sense? Or?
Yeah, because it makes sense. And I think my question was motivated because of the third point, which says that the principal takes the empirical distribution from this to be his proxy for the prior or something like that, right? I mean, it has to connect. So I think this says it, for instance.
I'm sorry, I think I missed the last part.
No. I mean, my question was just to see why is it that the principal is taking the empirical distribution from the output of the second point. I mean, so I think you answered the question.
Okay, yeah, I mean, so we are going to actually, okay, well, let me know as we go along if I can help to, fill in the details anymore. But let me set this up and we'll see how it goes. Okay. So the principal is going to accept this empirical distribution. So they're going to take the data, construct this empirical distribution, and they're going to use this empirical distribution to evaluate the expected payoff. One way of thinking about this is that, and let me just take that away for a second, is that there's going to be some ambiguity with respect to what the true technology is given the empirical distribution. This will certainly be true for small data sets. In effect, one way of looking at this assumption about what the principal is doing is to say that the principal is basically neutral with respect to this ambiguity. So you could think of them as an ambiguity neutral person. I thought of trying to formalize this a little bit more, but I didn't do it in this paper with respect to something analogous to risk neutrality in the sense that the principal is doing this many times. As they do this many times with many different agents, perhaps the sort of ambiguity washes out on average. I'm not gonna, we don't have that as part of the paper. We're just going to work with this assumption of them accepting the empirical distribution. There are some reasons to focus on the empirical distribution as opposed to other ones, but let me say that although we didn't do it in the paper, many of the basic ideas in the paper will go through just fine if you were to look at another distribution that the principal might view as being plausible. Okay, so in terms of plausible distributions, that we're going to focus on the agent. We're going to have an agent that's going to form confidence sets, and these confidence sets. This is perhaps a scary looking expression here, but the idea is very simple. Okay, the idea is that the agent also has access to the same data. They can also form this empirical distribution pi hat. But they are going to view as plausible a whole set of distributions. So this delta omega term is the set of possible distributions on output. They're going to look at all mu here, all distributions that are not too far away, roughly speaking, from the empirical distribution, where we're going to measure not too far away using what's called the total variation norm. So the total variation norm basically you can view this as a soup norm over the set of possible events in the sigma algebra. Okay, so we're looking at distributions which don't vary too much from the empirical distribution according to this norm. Now we don't use it very much in the paper, but another parameter that you can use in a problem like this is the agent's confidence that they demand. Okay, so the size of this confidence set for the data is going to depend on this parameter delta. You can actually view this as being analogous to sort of a null hypothesis testing exercise where we say the agent wants to have a guarantee of that we don't fall outside a particular set with probability greater than 5% or something like this. Okay. So the idea here is that we're setting this up in order to use some results from the literature on empirical processes. And this literature is going to allow us or it's going to give us some bounds that we can place on that we can use to bound the probability that one of these mu's falls outside of this confidence set for a given, or you use that probability as the agent's confidence level. That wasn't, I didn't say that very clearly. Let me go through a simplified example here. So here's an empirical distribution. I just pulled this graph off of Wikipedia. This is not the bound we use, but it's closely related to the style of bounds that we're going to use. Here we have just a kind of a generic problem here. Here we have a CDF given by this orange curve for some random variable x. The empirical distribution here is indicated by the blue step function. And then this inequality here, which is referred to as the DKW inequality, is a uniform bound on how far the true distribution f of x can be away from some empirical distribution f sub n of x. So the way this works.
Justin,
yes.
Sorry, just to interrupt. Can you just confirm what n over here is? Because if I'm not wrong, NE is the number of observations corresponding to some effort E.
Yeah. So n is going to So n is going to correspond to the number of data points. So okay. If you see in that second bullet point, we have the outputs labeled from 1 to n.
Okay. Sure. Okay.
Yep. No problem. And the N of E is just indicating that we can deal with different size data sets depending on the effort level. Okay, so this is one way of placing bounds on how far away the true distribution can be from the empirical distribution. These are non-parametric bounds, and throughout we're working with non-parametric statistics in the sense that we are not assuming any sort of parametric form for the true output distribution. So the way the DKW bound works is you calculate your empirical distribution, and there's kind of two ways of looking at this, but you have the number of data points, and this probability bound says that if you don't want your empirical the soup norm of the difference between your empirical distribution and the true distribution to be greater than some epsilon, then the right-hand side gives you an upper bound on the probability with which that violation will occur. Another way of looking at this is to say that if you want this probability to be lower than some amount, you can determine a corresponding epsilon with which that occurs. So that is the viewpoint that we take. In other words, the basic idea here is the agent is going to have the number of data points, and then they're going to demand a certain level of confidence delta in the data, and that's going to determine the width, in a sense, of the confidence bands on the distribution that they're looking at. So the epsilon here is determining how far these purple step functions are away from the empirical distribution, and that gives you a confidence set which includes all distributions that lie between those two purple limits. Okay. Now,
so Justin, very quickly, I mean, regarding the epsilon that you are talking about, this function, right? In the last page, last slide, yeah. So within the curly brackets, the moment your pi, the technology, the true technology is given, this epsilon is a function which we take as known henceforth. Is that right?
I'm sorry, could you say that again?
Yeah, I mean, what I meant is that given a number, NE and delta, the epsilon is now known, right? I mean,
yes. So okay. So let me so that the epsilon. So we have a data set. We know how many observations are in a data set. The agent is going to demand a certain level of confidence, which you could think of as saying that they want to be 95% sure of, and I'm going to tell you sure of what in just a minute. Depending on which probability bound you get, you're going to get a different epsilon. So if you were to use the DKW bound and you demand kind of 95% confidence, so to speak, that the distributions lie within this set, then you can back out the required epsilon given the bound here. Okay, so if you use a different inequality, a different bound, it's going to give you a different epsilon.
Right, thanks.
Okay. All right. So this when should I go to? I think I'm going a little slow here. I have until is it another half an hour or so? Is that it? Or?
Yeah. You have half.
Oh, okay. I'm sorry. Let me speed up. So I think in a model like this, it's important to spend some time setting it up and to think about the assumptions, because in effect, that is a large part of our contribution here, but I'm getting a little bit bogged down in the details, perhaps. Okay, so we entertained using the DKW bound. However, one of the important limitations of using a bound like this, and this is actually a limitation of doing something completely different, such as trying to use a central limit theorem or something like that. One of the limitations here is that the DKW bound is about a CDF of a random variable, but we want to think about the random variable that the agent cares about, which is wages. And these random variables are being determined endogenously in the model, and we don't want it to be the case that the principal kind of foresees the inference procedure that the agent uses and takes advantage of it in a sort of unrealistic way. So if we were to try to use the DKW bound, then the principal might try to leverage just the fact that they're using a particular bound or a particular inference procedure. And to the extent possible, we want the inference procedure to be sort of independent of the way in which the model is working. So what we did was we turned to probability bounds, just similar, very similar to the DKW bound, that instead look at bounding probabilities across all events in a way that is agnostic to the ordering of the wages, which is where the ordering of because the ordering of the wages is controllable by the principal. It's an endogenous factor in the model. Okay, so basically, what I want you to take away from this is we are going to the specific bound that you choose, and we're sort of going to be agnostic to the particular bound that you're going to choose. It's going to determine this residual epsilon in the problem. Okay, so the agent here, we're going to use incomplete preferences specification due to Bewley. This has been used more recently by Lepomo, Rigatti, and Shannon, which is a paper that I have a discussion on at the end, if we get there. But basically, the agent here is going to require that high effort is incentive compatible and individually rational for every technology that falls into that confidence set. So for every technology that is consistent with the data. And then there's an analogy here to kind of the agent doing something along the lines of a non-parametric null hypothesis statistical test, where shirking or no effort is the default action. So they want kind of complete confidence in the fact that effort is the right thing for them to do given their data set. It's similar in this criterion is similar in spirit to kind of max-min preferences. However, if you literally implement max-min preferences in this environment, you can potentially get some odd results. So max-min would be one way of implementing max-min would be to say that the agent has a confidence set for high effort and a confidence set for low effort. And across these confidence sets, they focus on the distribution that gives them the worst possible payoff. The issue with that is that when you're looking at incentive compatibility, you would end up comparing the worst possible payoff under high effort to the worst possible payoff distribution-wise to low effort, and you might give the principal an incentive to just make low effort look terrible, if that makes sense, instead of focusing on making high effort as attractive as possible, which is the kind of the effect that we're going to get under these preferences. Okay, so let me try to do this quickly. This is a point that I quite like, but it's a little bit minor with respect to the whole paper. There's an assumption. So one of the things you can do when you're critiquing a model is you can look for odd predictions, right, in the extremes. In the Holmstrom model, it is often assumed, if you're going to use it in a paper, that output has the high effort and low effort output share common support. And the reason for that is really that if there are any events which can only occur under low effort, the solution to the problem is trivial. All you do in the Holmstrom model is you pay a constant first best wage as long as you pay a constant first best wage across all the states for which high effort was in the support of the high effort distribution, and then you just punish the agent for any of those events that could only possibly occur under low effort, as much as you need to in order to slacken that IC constraint. Okay, and in some sense, the cause for this odd prediction in the Holmstrom model is this, so to speak, unrealistic level of precision. So if, for example, there were a level of output, if the level of output 3 could have only occurred under low effort, but maybe there's 100 different output levels, the Holmstrom problem is immediately trivial. And the reason is that you can just attach an arbitrarily low wage to the output level of 3 so that the agent would never, and that's enough to prevent the agent from selecting low effort. Now, in our model, we actually, because of the nature of the framework here, we don't have the same sort of drawback, or we don't, the same sort of case does not occur. And basically, instead of going through the everything here, let me just give you the basic idea. Let's take that example where output level of 3 could have only occurred under low effort, but now let's take the interpretation that instead of knowing the true distributions, we have only data about low effort and high effort. And the idea is that, like, we have this data point that only occurred under low effort, output level 3, and it didn't occur under high effort. And say, let's just hypothetically try to do the same trick that we did in the Holmstrom model. Let's try to pay the agent a really low wage under for that particular output level, and otherwise pay them a constant wage for all of the output levels that could have occurred under high effort. And the idea is that that doesn't work here. And it doesn't work because the agent is going to view that output level as plausibly occurring under high effort. So they're going to view it as being possible that they exert high effort and they do get that output level of 3. And they respond to that by kind of effectively placing some plausibility on the output level, effectively by assigning some probability to that output level. And as soon as the agent assigns some probability to that particular bad output level, high effort no longer becomes incentive compatible. Anyway, this idea is kind of codified here, but the basic idea is that we sort of resolve, just from the get-go, we resolve some of these oddities reflected in the Holmstrom problem by introducing some uncertainty about the true distribution for the agent. Okay, so for the model, for the main analysis, we didn't make these assumptions for the previous result. For the main analysis, we are going to, just to reduce the complication, but not really to do anything important in the analysis, we're going to assume that the empirical distribution has full support for each level of effort. This is just mainly to reduce the number of cases that we have to consider. The second thing that we're going to assume is that the empirical likelihood ratio, which is going to play an important role, is injective. And in other words, each event, each output state in the data is going to have a different empirical likelihood ratio. That's actually in our analysis without loss, because what you can do is if two events have the same empirical likelihood ratio, you're just going to end up combining them into one event. So you can relabel the events. We don't do that. We just work with this simplifying assumption. And then the third assumption that we're going to make is kind of a non-triviality assumption, and that is that the agent's confidence sets do not intersect. And the reason that's important is that as soon as the confidence sets intersect, meaning there's a distribution that lies in both of these confidence sets, you're not going to be able to incentivize the agent to exert high effort at all, because they need to, it's no longer going to be possible, according to the agent's preferences, to convince them that, that high effort is definitely better than low effort. Okay, so this is the principles problem as it stands in our model. We're going to next reduce this problem and simplify it. Basically, what we were saying is that we're taking a standard Holmstrom problem and we're replacing the IR and IC constraints with the requirement that they need to hold across all distributions in these confidence sets. Okay, so the first thing we want to do is we want to simplify the problem. Let's think through, we'll think about just how these distributions work quickly. So imagine some contract and we're going to just enumerate the states. We're going to play around with how we order the states for a minute to make the contract increasing with respect to these different states. Now, we're not saying that the contract is increasing with respect to output. We're just playing with the indexing of the output states. As long as the epsilon that we were talking about before is not too large, then this is just to give you a sense of what the kind of extremal distributions, or at one point we'll call these critical distributions, the form that they take. For low levels of epsilon, all that happens here is we just look at the high effort distribution, the one on the bottom. We're going to end up, the agent is going to end up basically subtracting that epsilon from the probability attached to the highest wage. We're doing sort of a worst case analysis here, and push all of that probability onto the lowest wage state. Alternatively, on the low effort distribution side, they're going to do the reverse. They're going to say that they're going to add epsilon L to the highest wage state under low effort, and subtract the corresponding amount from the lowest wage state under low effort. If we were doing a max min, those signs would be flipped on the low effort probabilities. Okay, as the epsilon grows, it gets a little bit more complicated. Basically, as the epsilon grows, we end up running into the bounds on valid probabilities. So at some point, for example, epsilon h will be large enough to make the probability of the highest state 0. And then at that point, we end up bunching the highest state with the next highest state. So we end up setting that highest probability 0, and then starting to subtract epsilon from the k-1 state. Okay.
I mean, is that where the graphs that you were showing initially, they start merging or something like that? I mean, with the four
yeah,
terms.
so it's what happens at the boundaries here. So it's when these purple step functions run into the lower and upper bounds.
No, and I'm asking about, there were these four utility graphs that you showed us initially, right? I mean, as your epsilon was increasing, something like that.
Okay, so here.
Yeah, those mergers. I mean, are these connected with the issue that you just talked of?
Yes. Okay, so basically, when those probabilities become 0, that's a sufficient condition for bunching the states together. But the bunching is going to happen before that, typically.
Oh.
Does that make sense? So when the epsilon is large enough to make the probability of the highest state 0, there's no question that the principal has to bunch the two highest states together. but they actually are going to do that before that.
Right.
Okay. So let me see, where was I? Okay. Okay, so the main reduction that we want to make in the problem is to say that basically in order to determine these distributions, the ordering of the wages is important, but it's endogenous in the problem, how you should order the wages. And our first result here actually is going to, and I won't go through the logic because due to time, but the first result is to say that actually the ordering of the wages in the optimal contract that's offered by the principal is actually pinned down by the empirical likelihood ratio. So if you just take that Holmstrom likelihood ratio and you plug in the empirical probabilities for each one of the terms, that's going to determine the ordering of the wages. Okay, so then what we do, that's our kind of first lemma here. And then what we do is we then reduce the problem that we had before, and we simplify it in three ways in a sense. Okay, the first thing that we're going to do is actually more convenient to work in utility space. I showed you that already in that picture. So what you do there is you can write the IR and IC constraints in terms of expected utilities, where the utility term here is the V term, and then rewrite the principal's payoff to be in terms of a cost of providing a particular utility. So there's a Grossman Hart paper that does this. I think it's 82 or something like this. So we're going to write everything in terms of utilities. Then we're going to remove those quantifiers on the confidence sets by imposing monotonicity on the states according to the increases in the empirical likelihood ratio. So we're going to order the states according to the empirical likelihood ratio, 1 to k, and then we're going to have a monotonicity constraint. That's that last constraint in that problem that says that the utilities have to be increasing with respect to the empirical likelihood ratio. And then once we do that, we can pin down what we call what's the extremal distribution or the critical distribution for the agent. That's going to be the pi star. The pi star hat, that's just a typo, ignore that. But pi star is the kind of the critical distribution for the agent. And what this does is this simplifies the problem. It actually makes it into a convex program as long as the C function is convex. And so it makes it actually very easy to solve on a computer. So that's what we can generate lots of examples. Like the graph I showed you earlier. And I will return to that graph in just a little bit. Okay, so our main research question here is how does the structure of the optimal contract vary with these residuals? So the residuals are going to capture the degree of confidence the agent has in the data. And we're interested in how the structure varies with them. So we already saw in that graph, for example, and I'll show you it again, that there's quite a bit of detail in the contract when the epsilons are low, and that the contract becomes more coarse as the epsilons grow. So the way that we capture this is through this somewhat kind of ungainly definition of a structure, but basically the structure, if you look at this example below, is telling you how the principal decides to separate the different states in the contract. So there's going to be what we call low wage contingency, which is the states that is going to be associated with the states that the principal pays the agent in the lowest wage in. I'm just looking at the last sentence here. And then there's going to be a high wage contingency. That's going to be how the principal bunches the highest states. And then there's going to be some intermediate states. So this structure is related to how the principal is partitioning the states. Okay, so given the nature of that problem that I wrote down previously, you can write down first order conditions. I don't want to spend too much time trying to interpret these directly for you, but basically there's these first order conditions bear resemblance to the Holmstrom ones, with adjustments, with two kinds of adjustments. One is for the fact that we have the agent making probability assessments in a way that's different from the principal. So the numerators and denominators differ. And then we have these additional sigma multipliers related to the monotonicity constraints. Okay, so just to give you a sense of what's going on, we're going to have this low wage contingency over which we're going to bunch the low wages together, perhaps. We're going to have high wages contingency in which we're going to bunch the high wages, and then we're going to have these intermediate states, which I'm calling non-extremal states here. And in the non-extremal states, the model's prediction is that essentially the Holmstrom's equation is satisfied. So the extent to which our predictions differ from Holmstrom is on the extremes, perhaps unsurprisingly. However, you should keep in mind, perhaps, and this was a difficulty in going through the actual work here, that these multipliers are endogenous, right? So they're being determined kind of globally across the problem, and so they are sensitive to how the bunching at each one of the endpoints is occurring. Okay. So the form of the optimal contract is as I've suggested here. So we have high and low wage contingencies. Those are it's at the lower and upper bounds that the monotonicity constraint is going to bind and bunch states together. That's where the coarseness in the contract is going to come from. These extreme states, because we're ordering the states according to the empirical likelihood ratio, correspond to the cases in which the empirical likelihood ratio is either large or small. These are exactly the states, according to Holmstrom's prediction, under which you would want to pay extreme wages. The difficulty here for the agent is that when you want to pay extreme wages according to the Holmstrom model, because of the denominator and the likelihood ratio there, these also correspond to states in which we have low probabilities. So when you add in this consideration of the agent wanting to be confident from the data, the agent ends up kind of discounting these low probability events, and that ends up, through the mechanisms of the model, leading the principal to bunch the states together. And one intuition for this is that the principal can only kind of convince the agent to exert high effort if the wages that they're going to pay for, when output is favorable with respect to high effort, occur in events that have high enough probability. And the way that the principal can get these events to have higher probability is to bunch them together endogenously. Okay, so there's our picture again. Basically one way to think about what's going to happen next is we have this idea from the picture that as epsilon grows, there's very, I think, clear intuition that as epsilon grows, the principal is going to have to start bunching these states together. But we're interested in the nature in which this occurs and the extent to which, for all possible kind of models that you might write down and assumptions that you might make as inputs, how does this occur, and how precisely can we describe the comparative static as epsilon grows? Now, we would like to say, in other words, we're trying to formally describe what's going on in this picture across all of the different possible assumptions you might make about utilities and so on. Okay, so one of the things you can do, and this is kind of the most straightforward thing you can do, is look at limiting results. To describe the limiting results, we're going to define 3 events. Okay, let me tell you intuitively what these are. We have omega hat L. So omega hat L is going to be all the output states in the data that have a negative empirical likelihood ratio. So you can think of these as, broadly speaking, these are the states that indicate that low effort is better than high, that low effort was more likely according to the empirical distribution. Then we have omega H, which is the opposite, the states under which empirically high effort was more likely to have been selected. And then we have this kind of edge case in which the empirical likelihood ratio is 0. So that only occurs when the probability, the high and low effort probabilities for that particular state are exactly equal to each other. You can think of that as, you know, being almost a zero measure event in a sense. Now, we're going to call a contract naive if essentially we're going to call a contract naive if the principal pays the agent in a more or less binary fashion, where they pay the agent one wage for all the negative likelihood ratio states and a different wage for all the positive likelihood ratio states. We're trying to be a little bit careful here because we're admitting the possibility that there are some states in this omega 0, but as long as omega 0 is empty, then our naive contracts are going to be binary. If omega 0 is not binary, then we need to admit kind of ternary contracts that pay 3 different wages. So our kind of first main proposition here, and this is just what we saw exactly in the picture, if the agent's confidence in the data is sufficiently high, which is going to occur when they have lots of data, or you manipulate that delta term in the correct way, then the contract is going to be fully detailed and essentially agree with what you might call the empirical Holmstrom contract, or the Holmstrom contract that you would determine if you just used the empirical likelihood ratio and solved Holmstrom's problem. Alternatively, on the other extreme, when the confidence in data is sufficiently low, the optimal contract will be one of these naive types, which in general will be a binary contract, just like the picture we showed. Okay. A way of describing this contract is to call it what we call a capped bonus contract, which is essentially is just what I've been describing. You have a low wage contingency in which you bunch some of the states for the low wage, a high wage contingency, and then all of the other states are left distinct. And in general, we can show that the optimal contract is a capped bonus contract, just like that one. The last thing that I'll do for you today is just to talk about comparative statics. So comparative statics is if we have the limiting results, one is being like all the way at one side of the graph and the other one is being at the other endpoint of the graph. What can we say about what goes on in between in general? To do this, we're going to introduce 2 more events, omega L and omega H. And basically, I won't go through how we construct these, but omega L and omega H are going to be based on conditions on the multipliers that you can derive through using the first order conditions of the reduced problem. And basically, let's just focus on the low wage contingency L. The low wage contingency, what that is that's the set of states that we're bunching at the low wage. So it's a set of states for which we're paying the lowest wage. We can show that this low wage contingency has to fall between 2 extremes. So these are putting bounds on the set of states that we're bunching. At most, we're going to, the low wage contingency is going to include all of the output states in that omega hat term that we introduced before. That's as part of the naive contract. And then the omega L is capturing all the states that we can prove across all possible utility functions must be bunched. So our proposition here is just saying that we can put bounds on the states that fall into these low and high wage contingencies. Now, in terms of comparative statics, these events, which I haven't defined here in the presentation, omega L and omega H are increasing in the residuals. So as the agent becomes less confident in the data, that's what it means when the residuals increase, the number of states that must be bunched grows. The naive states are not, because these are the hat omegas are determined just by the empirical likelihood ratio. They're effectively constant in the residuals because the empirical likelihood ratio is not changing as we're doing this comparative static exercise. Now, what we were able to show from a comparative static perspective, and this is kind of our main result in this part of the paper, is that as you play around with the difference in effort costs, delta IC, you can basically hit either one of these extremes. In other words, if you don't take the stance of, I don't know what the difference, I'm willing to not that I don't know, I'm willing to attain many different effort costs, then both of these contingencies are always going to be possible in the problem. So what we were able to show, and we didn't include this in the paper, but we were able to find some odd examples where the principal would, as epsilon grows, bunch some states together, but then unbunch them later. So we had hoped initially to have a cleaner result along the lines of like the number, if the principal bunches states 1 and 2, then as epsilon grows, they always continue to bunch states 1 and 2. And it turns out, interestingly enough, that you can come up with some weird utility functions for which that's not the case, that they might bunch some states together and then later decide to unbunch them after epsilon has grown some. Now it's strange. The types of things you have to set up in order for that to occur are strange. What we're showing here is that in general, you can't do any better than improving on these bounds, as long as you're willing to entertain many different differences in effort costs. So in other words, if you make delta IC, the difference in effort costs, large enough, you're going to hit the maximum detail bound. Now, from the Holmstrom standpoint, and I'll just leave this as my last slide since I'm almost out of time here. From the Holmstrom standpoint, as I suggested early on, the detail in the contract is actually coming out of the fact that the agent is risk averse. It's in effect we know that we need to pay the agent. We need to expose the agent to some risk in order to get them to exert effort. But we want to minimize the amount of risk that the agent experiences because of the risk aversion. And I thought this was kind of a neat trick here. Basically, in our model, but also in a Holmstrom model, as you make the difference in effort costs large enough, you're effectively making the agent more risk averse. So holding the utility function constant, making the difference in effort costs is effectively making the agent more risk averse, because what you're doing is you're forcing the payments further and further apart as you increase the difference in the effort costs. And what this does is it forces down the margin utility of the high payments relative to the low ones. So you can think of this as analogous to increasing the curvature in the utility function. It's perhaps weird to play around with the delta IC here as in terms of generating our previous result, but it's actually doing something analogous to making the utility function, giving the utility function more curvature. So this detail in our model as well is intimately related to the degree of risk aversion that the agent has. We're in effect, with respect to the Holmstrom model, adding this counteracting force with respect to the inference problem that the agent has with finite data. And what this result is showing in a way is that you can overcome this incentive to bunch states together as long as you're willing to make the agent more and more risk averse. Okay, and then lowering the IC constraint kind of has the opposite effect. Okay, so I think I'm just about out of time, so I will stop there. If there are any quick questions, I could maybe address them. And this is kind of a complicated paper, so I hope everything I said made some sense.
Yeah, thanks. So any questions? No questions. If none, then maybe I can ask one. So we recently read this Carroll's paper on robustly linear contracts in this Borel-Hamming problem. So, I mean, can you remind us, like, what are the differences in his approach of dealing with the uncertainty about I think in his model, the principal was uncertain about the technology that the agent has. Is that correct? So how does that relate to your problem, your way of attacking this?
Yeah, so Max and I, the paper we're currently working on is actually very closely related to the Carroll paper, but let me talk about it with respect to this paper. So Carroll assumes that that there are a set of technologies that the agent has access to that are known by the principal. Okay, so instead of there being uncertainty about the technology itself, like we have here, there's a set of technologies that are known. But then in that model, the principal entertains that the agent might have access to some completely arbitrary technology that lies outside of that set. So there are in effect no constraints. Well, not no constraints. There's an incentive compatibility constraint, but there are very few constraints on this unknown technology from the principal's perspective in that model. Another very important distinction, it actually comes up in relation to our paper and this Lipoma, Rigatti, and Shannon paper, is that in both Carroll's paper and this paper, the agent is risk neutral.
Yeah. Okay.
And you really can't. The question that we're trying to address here doesn't really arise in that case at all. Because in the risk neutral case, we already know that kind of the Holmstrom prediction allows for coarse contracts, as we're saying it, right? So you really need to introduce risk aversion to get out, if you want to get at this criticism, so to speak, of the Holmstrom prediction to pay in this finely tuned, detailed way. Does that sort of address?
Yeah. Thanks for reminding. Any other questions? Okay, great. Thanks a lot, Justin. And so there'll be some students who will be talking to you, and they'll stay on, but others will be.
Okay. Thank you very much. Thank you for the invitation, and thank you for the audience.